Hello, welcome to a podcast for gas laws. Today's podcast is a review for your test. This is a basic overview of every type of problem and how you work them step by step. So you can go ahead and fast forward if you don't like the problem I'm doing and you want to go look at another one. First of all, you need to have this memorized. You need to know all your standard pressures, that 1 atmosphere is 760 millimeters of mercury, 760 torr, bad radio station 101.3 kPa. You need to know that your standard temperature is 273 Kelvin, okay? And that's why you add 273 to Celsius to get a Kelvin temperature. We'll talk more about that at a different time. You need to know your ideal gas law is PV equals nRT, Parkview, not RT. And to get the combined gas law, all you do is solve that PV equals nRT for R, if you forget it. And that is PV over NT. And so all you do is put ones here, and then if you change the conditions, it's simply PV over NT again, 2, 2, 2, 2. You need to know that Boyles is the vice president, and that his relationship is an inverse one, indirect. That Charles watches TV, he's got a direct gas law. Gay-Lussac is also direct, and he drives a Petit Cruiser because he is from France. Not really, but hey, you know. And Avogadro is also a direct guy, and he drives a van. V, right here, A, N. Now, how do you get Boyles, Charles, Gay-Lussac, and Avogadro? You look at the combined gas law, remember? And so, for instance, for Boyle, which is the vice president, you go ahead and you say, hey, there's no moles or temperature mentioned in my problem, and that's your formula. All right, if you were to do Charles, you would say, hey, there's no pressure or number of moles mentioned, and there's Charles' law. If you were to do Gay-Lussac, then you would say there's no volume mentioned and moles, or they stay the same, no volume and moles, and there's your formula. And for Avogadro, you would do the same thing, but you would do it for V and N. So you would say no pressure, no temperature, and you go ahead and divide, right? And then same thing over here, no pressure, no temperature. You go ahead and divide. Okay? All right, so here we go. Number 1. A bag of potato chips is packaged at sea level, 1 atmosphere. That is a pressure, the first one I ran into, and has a volume of 315 milliliters. That's my first volume I run to, and they are connected because they are connected by this connector. If this bag of chips is transported to Denver, 0.775 atmospheres, there's my second pressure, what will my new volume be? Well, there you go. Okay, so what are you dealing with? Pressure and volume. So whose law is that? You say Boyle, and I'm going to say it's not direct, it's an indirect relationship. So that's your choice. If I gave you a graph, the graph would look like this. And it could be volume or pressure, either one on either axis. Same difference. It's still an indirect relationship. Okay? All right, now, how do you set this up? You think of your combined gas law, P1V1 over N1T1, except guess what? I'm not going to use the N and the T. Are there moles mentioned here? Nope. Is there temperature mentioned here? Nope. But that doesn't mean they're not present. It just means I'm not telling you what they are. So I don't need these. So I'm going to just go ahead and do P1V1 equals P2V2. See, I'm just leaving the N1T1 off and the N2T2 off. So now all I do is plug my values in, and I say that 1 atmosphere, right? And you can write your units if you want to. I'll do it for this first problem, but you don't have to. Once you set up your formula like this, then you're fine. And a volume of 315 milliliters, okay, equals, what's my second pressure? Oh, I know my second pressure, 0.775 atmospheres times V2. Now, I like using V2. You can use X if you want to, your choice. And I'm going to go ahead and be a good person here so I get my answers correct. I'm finding my new volume, which is V2. If you get things wrong, you can write it down over here so you remember. I'm going to go ahead and label my units ahead of time so I don't forget to do that. Now, when you do your math, what do? You divide both sides by 0.775. and I do 1 times 315 divided by 0.775. Okay? I got to calculate it for a more complicated problem. Right, this cancels. And when I do my math, I get 406 milliliters. That's my answer. All right, problem number 2. I have 45 liters of helium. That's a volume. In a balloon at 25 degrees Celsius, that's a temperature. And I increase the temperature of the balloon to 55 degrees Celsius. That's a second temperature. What will the new volume be? Well, sticking to what I'm going to do over here, I'm labeling what my volume is. I look back and see that my volume here is in liters, so my answer is going to be in liters, so that way I don't get any points off. And I ask myself, okay, volume and temperature, who's that? Oh, that's Charles. Good old Charlie, right? So Charles' law is a direct relationship. And his graph, if you had one, would look like this. And again, with temperature or volume, depending on what you were manipulating, right here. Okay? Now, what is my equation? Well, here you go. P1V1 over N1T1. Are moles mentioned? No. Is pressure mentioned? No. Does it mean they're not present? No. There's a temperature, a pressure, a volume, and number of moles. I just don't mention those because they don't change. Okay, last time I'm going to say that. So I don't keep boring everybody who does understand this. And if you don't understand that, then you can write P1V1 over N1T1 for each problem, and P2V2 over N2T2 for each problem, and then just cross out the variables that you don't have. So I know for a fact that I'm not using pressure or moles, so I'm going to go ahead and put volume over temperature equals volume 2 over temperature 2. That's the equation I expect you to write. And now you look back at your problem and you say, okay, I have 45 liters, and I have 25 degrees Celsius. I need to change that to Kelvin by adding 273, and that's 298 Kelvin, and that's going to go right here. And again, I'm just putting units for these first couple problems, okay? And by the way, if you don't write this right here, and you just show your work for this, and you just put your answer right here, right? That's fine. That's showing your work. All right, now, what's my second volume? Oh, I don't know that. What's my second temperature? Well, I have 55 degrees Celsius, and I need to change that to 273. If I do that, that equals 328. Okay? Now, how do you do this? I'm going to show those of you who don't understand really quickly, okay? Because there's nothing worse than knowing how to do this stuff and then being shaky in the math. So I'm going to take 45 liters, right? Times 328, just to show you, equals 298 times V2, or X. Okay, you cross multiply. Divided by 298 on both sides. My answer is 49.53. This cancels, and my math gives me that. Now, very quickly, so I can show you, right here, I'll get the same thing without writing all that out by doing a quick shortcut. I'm not going to choose this right here. I'm going to, right, that cross multiplies. I'm not going to pick that one. I'm going to pick 45 times 328. And then I'm going to say, okay, that's equal to V2 divided by 298, so I'm going to take 298 and just divide by it, right there. And that'll give me my V2. Okay? All right. Number 3. A toy balloon has an internal pressure of 1.05 atmospheres. So here's my first pressure. It is a volume of 5 liters. Now, if the temperature where the balloon is released is 20 degrees, so that's the first temperature I run into. What will happen to the volume? There's my V2. When the balloon rises to an altitude where my second pressure is this, and my second temperature is this. So, what law is this? Pressure, temperature, volume. Oh, this is my combined gas law. Now ask yourself, do they mention moles? No, but the balloon is full, and it's released, and doesn't say anything about gas coming in or out, so you don't use moles. So your equation is going to be P1V1 over T1, leave the N off, P2V2 over T2. Now, This is more complicated because I got a bunch of laws going on at the same time. That's why they call it the combined gas law. So I'm going to go ahead and fill in my information, and I have 1.05. Now, guys, I'm not going to write units anymore, okay? I'm just going to fill in my pressures and my volumes. 5 liters. Okay, and my first temperature, because I need to change this to Kelvin, right? 273 and 20. That's 293. Okay, and then I'm going to go ahead and put my second pressure, 0.65, times I have no idea. Now be careful, this is a negative 15. So 273 and a minus 15 is going to give you a number less. It's 258. Okay, now what happens when I do my math? There you go, make my 8s clearer. When you do your math, you take 1.05 times 5 times 258 divided by 0.65 and 293. Okay? So when you do your math, you come up with 7.11. Now let's think about this. I'm solving for a volume. That's why I like leaving my V2 here. Okay, I don't have to write it over here. For you, you might have to write it over here, but for me, I'll know it's V2. I look back at my problem and I say, oh, there you go. It's in liters. Number 4. A commercial airliner has an internal pressure of 1 atmosphere and a temperature of 25 degrees Celsius. And I know this is gas laws. Why? Because I'm on a gas laws test. So I'm going to go ahead and change this right now. Okay? If the temperature of the airliner drops to 17 degrees, I'll get my T2 here. So it's my T2. 273 and 17. Okay, so that's 290. And these are both Kelvin. What's the new cabin pressure? Okay, whose law is this? Pressure, temperature, that's Gay-Lussac. And that French guy is a real direct dude. Right? Okay, so now what? I look at my combined gas law, I leave off volume and moles, and there's my relationship. Okay, so I'm going to plug my numbers in. I don't need to put units. If you really want to, go for it, but I'm fine with it because you know what they are. And I'm going to go ahead and put my pressure, my temperature in the correct spot. This is my second pressure, which I don't know. And I've got my 290 right here. And when I do my math, 1.0 times 290 divided by 298, I get 0.97. Now what am I solving for? Pressure 2. And those units are in atmospheres from pressure 1, and so that's how I label. Remember, if I'm going too fast, you can pause and do the math, okay? But I'm just trying to get through this so it's not super long. Number 5, how many moles of gas, doesn't say what kind of gas, does it take to occupy, so moles is N, right? Occupy 120 liters. There's my pressure, and I've got a temperature. Now I go ahead and do P1, V1, and all that stuff, okay? Now look at this. What's different about this? This means that I don't have a change of anything. I'm not changing volume, temperature, or pressure. So my equation is PV equals nRT, or the ideal gas law. I can write. Right? The ideal gas law. And that's more complicated. Okay? So, what am I going to do here? My PV equals nRT. I'm going to solve for N. So, Parkview not RT becomes this when we solve for N. Okay? So I'm going to go ahead and plug things in. Now, the thing you have to remember is I'm going to give you R. And you have to look at your units for R. And the units for this R that I'm giving you is liter atmosphere, or liter atmosphere mole in Kelvin. That means that everything in your problem has to match. Okay? So let's look and see what I mean. I have a pressure. That's my first variable right here. So I find my pressure, and it's 2.3 atmospheres. Well, look at that. It matches, doesn't it? It matches atmospheres. So I can use it. If it didn't, I'd have to change it. We'll do one of those in a minute. All right, what about volume? Where's my volume? my volume is 120 liters, and that matches also, right? That's liter atmosphere. Okay, so I'm going to go ahead and multiply them. All right, now what's R? Well, R is this. Y? Y is pi 3.14. You memorized it, so I'm going to give it to you. So that's what R is. Okay, or there's a decimal there. And what's T? Well, T has to be in Kelvin, but it always has to be in Kelvin because we're doing gas laws. And look, they give it to you in Kelvin, so be careful. Don't add, right? Don't add that 273. So this is going to be my number moles. So I'm going to go ahead and label moles over here. If I want to put my variable over here, I can, right? N1 or just N. Now, what am I going to do to get this? I'm going to go ahead and do my math, and I get 9.89 moles. Okay? Number 6. I have a 0.64 mole sample. There's my N. I've got a temperature, 12 degrees Celsius. I'm going to go ahead and change that right now. And I'm just changing this right now, guys, because I know I'm on a gas law sheet. Okay? I know I'm doing gas law stuff. I can add. If I wasn't doing gas laws, I wouldn't change it to Celsius to Kelvin, but I know I am. Here's my volume. What's my new volume at standard temperature and standard pressure? Okay, a lot of information going on here. So what's changing? My temperature's changing and my volume's changing. Do they give me an initial pressure? No. So I'm going to cross this off. Do they change the moles? No. So I'm going to cross this off. So now whose law is this? Looks like Charles to me. How come? Because he watches TV. He's a direct dude. And so I do V1 over T1 equals V2 over T2. Gotta remember to change my temperature to Kelvin. Okay, so which I did. So I'm going to take 4.3 liters. I've got 285 equals V2 over, okay, wait, what's my temperature? They don't give me a temperature. Oh, but yes, they do. What's the standard temperature? You have it memorized. 273, right? And so when you do your math, you end up with 4.11 or 4.12, and that answer is in liters because you are solving for V2. How do I do that? 4.3 times 273 divided by 285. All right, if I place 3 grams of nitrogen, okay, oops, I left some stuff off, didn't I? I should say in a 350 ml container, oh well. At a temperature of 25 degrees Celsius, what will the pressure of the resulting mixture of gases be? Well, if I just look at this now without labeling, they only give me grams, they only give me volume, they only give me temperature, and they want to know the pressure. So guess what? This is the ideal gas law. How come, folks? Do you see them changing anything? No, you don't. So it's more complicated, right? So part view, not our team. And again, R is equal to 0.08206. And again, every once in a while you might see 0.0821. That's because that rounds it up. Okay, so if that's ever given to you, then that's why. All right. So now, how am I going to set this up? Well, what do you have going on here? You have 3 grams of N2. And by the way, what am I solving for? Pressure. So pressure equals nRT over V. Okay. Now, I've got 3 grams of N2. Where's grams in this thing? I don't see grams here, do you? Remember with R, I love R because you got to match it. Well, the closest thing to grams is moles. So I'm going to take 3 grams of nitrogen. Remember, if it said nitrogen, it didn't say N2. You know it's a diatomic, right? G-N-U-N. All right, so I've got G here, and I've got moles up top. How many moles in that mole hole? 1. And in nitrogen's box on the periodic table, it says 14.01. So it's going to be 28.02 grams, because I double it, right? Click, click, because there's 2 of them, right? All right, I'm going to do my math, and that math tells me that I have 0.107, and that's moles. So that's going to go right here. Okay, and again, if you don't want to label this 0.107 right here, that's fine. As long as you put your answer in the equation, I know and you know what you're doing. What's R? 0.08206. What's T? Well, 273, right? So that's 298. Some of you are starting to memorize that. And that's my volume. And by the way, if you notice, what am I doing? I've got grams, but I need to change it to moles right here. Right? I have Celsius. I got to change it to Kelvin. Right? Okay. And what am I finding? I'm finding pressure, which, by the way, is going to be in atmospheres. All right, below the line right here. Why is it in atmospheres? Because that's what's right here. And now I look for my volume, and I see that my volume right here is 350 milliliters. Ruh-roh. That doesn't match liters, does it? So how do you do that? Well, you can do it two ways, and you need to know both. You can take 350 milliliters, and that good old King Henry died Monday drinking chocolate milk, whatever. You go 1, 2, 3 back, and that changes it to liters. So 350 milliliters is equal to 0.350 liters. I'll put that right here. Or you have to be able to recognize that I can do it like this. Oopsie, sorry. I don't want milliliters. I do want liters. Liters are bigger, and there's 1,000 in it, which tells me to my decimal place 3 places back, and so you get 0.350 liters. And when you do your math, you get 7.48 atmospheres. All right, now, this is Dalton's Law, and there's a separate podcast on that if you'd like to look at this. I'll tell you right now. And the reason I know it's Dalton's Law, so it's none of these right here, is that I have a total pressure, right, of a mixture of nitrogen. Let me go ahead and use a different color here. I have a total pressure. Okay, this is not good. Come on. Pick the red, and there we go. Total pressure of a mixture of nitrogen, carbon dioxide, and oxygen. So I have a balloon or a container or something, and I have nitrogen, carbon dioxide, and oxygen inside. The total pressure is equal to 150 kPa. That's my total pressure. And they write it like this, right? Now, what do you know? They're asking you what is the partial pressure of oxygen if the partial pressures of the nitrogen and carbon dioxide are 100 kPa and 24 kPa. So you know that this is true. You know that the total pressure is equal to the pressure of carbon dioxide. Actually, let me go back here a second and let me list them in order of how they're given in the equation. You don't have to, but it helps. Pressure of carbon dioxide and the pressure of oxygen gas. All right, now what do I know? They tell me in my problem that carbon dioxide is 100 kPa, and they tell me that my nitrogen, oops, I read that wrong, didn't I? In order, respectively, nitrogen is 100 kPa, and carbon dioxide is 24, right? That's what respectively means in order of how I tell you. Plus X. Now what's my total? My total is 150. So all you do here is solve for X. And when you solve for X, you get 26 kPa. And that's the pressure of oxygen. And you know that because when you put 26 kPa in here, it all adds up when you add 26 and 24 and 100 to get 150. All right? Now, this is collecting a gas over water. If you need review on this, you can go to the podcast on it. Okay? So this is another Dalton's Law. It's a real world application of it. So again, it's none of these. And if it's collected over water, that was our key term, collected over water. That signals us that that's a different version of Dalton's Law. And what that signals us is that we have the total pressure equal to the pressure of the dry gas, whatever that gas would be. That gas is going to change, plus the pressure of the water vapor. And the pressure of the water vapor is going to change because the temperature they give it to us at is going to change. Now, what do we know? We know that we have hydrogen gas, okay? That means I have some kind of things here and it's producing hydrogen. Right, the hydrogen gas is going into this bottle. This bottle here was full, remember? But now it's not because all this gas is bubbling in here and the water's going down. As the water goes down, the gas level goes up, and inside here, inside this container is hydrogen gas, because that's what it says right here. So this dry gas was just hydrogen in this case, and water vapor. So there's two gases. That's what's inside this container. And they're bonking all around and hitting the walls of that container. In the meantime, the atmosphere is hitting the walls of the container too. And as long as you see a glass bottle, you know it's not exploding or imploding. And so therefore you know that the pressure inside is equal to the pressure outside, right? This is the outside pressure, and this total is the inside pressure. So outside equals inside. So what's true? If you look, sorry, I'm tapping here. If you look, they give you everything you need, okay? They give you 748.9 torr. What's that? So in a different color. Come on, select it. There you go. 748.9 torr. That's my total pressure outside and inside. Now, what do you want to find out? What's the pressure of the dry gas? So that means they have to give you the missing piece. They're telling it's at 27 degrees, and they tell you here at 27 degrees, the pressure of water is 26.5 torr. Okay? So what are you trying to find? X. X plus 26.5 equals 748.9. And when you do your math, you get 722.4 torr. It's that simple. Okay? Now, they don't always give you the pressure of water. They may give you the temperature and give you a table to look at, a chart. So again, you can look at the podcast on that, but that's how you do this. It's just a special version of Dalton's Law. The dry gas and the water, because that's what's in here. They give you this. They give you this, always, and you always are asked to find this. Okay? Alrighty. What's the partial pressure of carbon dioxide in a container that holds 5 moles of carbon dioxide? So let's make our container. Okay, I'll make a balloon. That works just as well as anything. I've got 5 moles of carbon dioxide. I've got 3 moles of nitrogen. And I've got 1 mole hydrogen. Okay, that's the facts. And the total pressure is 13.05 atmospheres. That's my pressure total. And what do they want to know? They want to know what's the partial pressure of carbon dioxide. Well, we're going to go ahead and find the partial pressure of everything, okay? So how do you do this? Again, if you don't know how to do these problems, you can go ahead and look at the other podcasts. But if you look at this, why does a balloon stay inflated again? It's because all the gases inside are hitting the walls. So how many total moles are here? Well, 5 and 3 and 1 is 9 total moles. So 9 total moles of gas, and the combined gases, carbon dioxide, nitrogen, and hydrogen, is equal to 13.05 atmospheres. That's how many moles total are bonking around in that balloon, keeping the walls of that container inflated. And they want to know how much gas is, how much pressure the carbon dioxide exerts. So let's go ahead and do this. So what do we know? We know that pressure total equals the pressure of carbon dioxide plus the pressure of nitrogen plus the pressure of hydrogen, don't we? And what do we know? We know the total pressure is 13.05 atmospheres. So, how do we figure out carbon dioxide? Well, we just said that the moles hitting the sides of the balloon are equal to the atmosphere, the total pressure. So what's that mean? That means if I look at carbon dioxide is exerting a pressure of 5 moles out of the total 9 moles, right? Isn't 5 moles of carbon dioxide out of the total 9? That times 13.05 is equal to the pressure of carbon dioxide. You put the part moles over the total moles because that's the fraction of it. It's called a mole fraction. And when you do that, I get 7.25 atmospheres when I solve that problem. That's how you do that. Now, how would you figure out the pressure of nitrogen? Well, the pressure of nitrogen is what? 3 moles of nitrogen out of 9 moles total. That's what part of the total pressure it is. So you take 13.05 atmospheres and multiply it by that mole fraction, and you come up with 4.35 atmospheres. Okay? Now how do you do hydrogen? Well, when you do hydrogen, you do a similar type of problem. And actually, I guess I should leave that up. Okay? And I'll just do the hydrogen over here. I'm going to erase the balloon. Okay? That'll work. Only so much room on these boards, you know? All right, so to do hydrogen, I would take 1 mole of hydrogen out of the total 9 moles times the total pressure, and that's what part the hydrogen is out of the whole thing. And if I didn't know it, I could go ahead and subtract, but it's 1.45 atmospheres. Now the answer to this question was just the 7.25 atmospheres for carbon dioxide. But I thought I'd show you how to do all of them. Okay? And this, my friends, is another Dalton's Law. But it deals with mole fractions. And repeat after me. Moles are pressure. I know it's not the same, that's not that's correct English, but the number of moles that are in this balloon is equal, they are the pressure in the balloon. So total moles equals total pressure. All right? Okay, moving on. Manometer problems. Now, when you do these, you have to think about which side is pushing harder, because that side has a larger pressure than the other one. So if you look at this diagram, what's true here? These levels are equal. So no one's winning. This is open to the outside. It's not always open, but you can look at the manometer podcast, but it is in this case. And so if you look, what's true about this gas? This gas, all these molecules are hitting this right here, and they're pushing down on that mercury. Okay? And all the particles from the air are pushing down on this level of mercury, and no one's winning. No one. Okay? So if I told you right here that there's 0 difference, that'd be the difference in the height. Is there any difference in the height of these mercuries? No, they're equal. So that doesn't apply in this case. And so what would be true? The pressure of the gas would be equal to the pressure of the atmosphere. So if you knew this was 720 millimeters of mercury, and I wanted to know what the pressure outside is, I would tell you that the pressure of the gas inside, because the gas is always in here, that it's equal to the atmospheric pressure. And I would know because these levels are the same. Now, let's look at this problem. Okay? Problem 11 on your sheet. You have a height. And the height, I'm going to tell you, is 30 millimeters of mercury. Okay, that's given. Okay? Now, what else is given is that there's 650, and we'll go ahead and just call it millimeters of mercury, that this is 650 millimeters of mercury out here. They tell me that. Okay, so in the blue is what's given. But you've got to figure that out yourself. So I'm going to go ahead and write in red what we're finding out. So what do you see? I see that levels of mercury are not the same. As a matter of fact, I see that this side is lower than this side. That means that the atmospheric pressure is pushing harder. That means that the inside is smaller than the atmospheric pressure. And so therefore I take 650 and I subtract 30 from it, and I get 620 millimeters of mercury for the inside, which makes sense because the atmospheric pressure is pushing harder. Do you see how it actually is pushing on this level, making it go down further than this level by 30 millimeters of mercury? So the answer for the pressure of neon is 620 millimeters of mercury. That's what's inside. All right, let's look at another problem. Who's winning? This is winning. It's winning the pushing war. Okay? So this is pushing harder. All right? Now what do we know? Let's say that this is given to you. Okay? Let's say that the pressure outside, the pressure of the gas is 730. That's given. Okay? And this is on your sheet. I just didn't type it on my podcast. And this is given. So we know that this is equal to 40 millimeters of mercury. And with the pressure of the neon, okay, this is neon in here or whatever gas, doesn't matter what gas it is 730 millimeters of mercury. Can you really read that? Okay, so who's winning? Well, the outside's winning. By how much? 40. That means this is a bigger number. Bigger than 730. By how much? 40. So you add 730 and 40, and that is equal to 770, and that's the pressure of the atmosphere. Okay? All right. And that's millimeters of mercury, right? All right. Now let's look who's winning here. Whoops. I put the wrong diagram in here, guys. I'm so sorry. That doesn't work. So let's fix this, okay? I'm going to go ahead and blue here. Sorry, this is squeaky. So I'll make it look like this, okay? So this side's higher. And we'll make this gas, so it fits the picture. This gas is gray. There you go. That works. Okay, now who's winning? The inside is winning, isn't it? It's pushing harder. How do you know? Because the level of mercury on this side is lower and this side's higher. So this is pushing harder. All right? Now, I give you that this is 825 millimeters of mercury. That's the outside. I give you H3, which is 60 millimeters of mercury. And I ask you to find the pressure of the gas in here. And we'll just call it neon in this case. Doesn't really matter. What's the pressure inside? Well, it's larger than 825. How do you know? Because it's pushing harder. That means you take 825 plus 60 and you add them. And you get 8. I can do this. Oh well, 885. That's your answer. Okay? All right, let's do another one. Let's do one you have to draw it. I have an open manometer, it's filled with mercury. Okay, so that's what I assume it would look like right there in front of me. The mercury level is 12 millimeters higher on the side open to the atmosphere. So it means I'm going to take this and I'm going to put it 12 millimeters higher. Okay, not the same color, but hey, you get it. Okay, so if it's 12 millimeters higher on this side, right, higher on this side than on this side, then who's winning? The inside's winning, it's pushing harder. So this is larger. All right, this is smaller. And there's a difference. All right, so I'm going to stop for a second.